we're going to do the Wilkinson divider too. The resistive divider is this one, where you basically are going to have a series of resistances that hit the center point here. Do it this way. All these have a value of Z naught over 3, Z naught over 3, Z naught over 3. And this is port 2, this is port 1, and these are going to be like this. So he has this. Now, I want to tell you this particular, yes?
Would you mind putting that on? Sorry.
Yes. Is he here?
He's here.
Thank you. Thank you. All right. This is one where all of a sudden he doesn't give a voltage, he gives a power. Everybody with me on this one, class? So with that in mind, first we're going to get the S parameters. So this has got Z naught here. It's port 1. That's port 2. This is port 3. All with characteristic impedance Z naught, right? So the whole idea with this divider is there is no reflection. Remember we went through this? If we look at this, the characteristic impedance looking in here is Z naught. When you add Z naught over 3, then you have 4/3 Z naught here. Do you all follow me? At this point, looking that way, you're going to have 4/3 Z naught. Everybody follow me on that? Just from the center point here, looking towards port 2. Everybody understand that? All right, now that's 4/3 Z naught. It's the same looking this way at port 3, right? Do you all see they're in parallel? So 4/3 Z naught in parallel with 4/3 Z naught is 2/3 Z naught. Do you all agree with me? All right, then when you add Z naught over 3, you get Z naught looking in here, which means the reflection coefficient at all these ports is 0. And that also means S11 is 0. This means S22 is 0, and this means S33 is 0. Do you all follow me there? Now, if the reflection coefficient is 0, the transmission coefficient is 1. Do you all follow me? And the reason is you add 1 plus reflection to get transmission. So the transmission is 1. And that means when we want to find the output signal on these ports, it's really voltage division. Does that make sense to everybody? There's no multiplying by the actual transmission coefficient. So the voltage division looks like this. If this is port 1, and I have V1 plus coming into it. Well, now that goes through a voltage division caused by this. And then it has Z naught over 3. And then I'm just going to put it as Z naught here, right? And then it has Z naught over 3. And then I'm just going to put Z naught here to ground. Now I'll explain why in a second, but does everybody follow me that Z naught right at the end there when I'm pulling it down to ground really represents the resistance, the impedance seen right at these 2 points. Does everybody follow me on this, class? Give me a show of hands to make sure. All right, I know you just had a test. I'm trying to do this simply. You don't see it? All right, he's tired. He's about ready to take a nap. Anyway, the idea is this. Make this problem as simple as possible. So do it this way. We want to figure out how much of the voltage here gets to this point, right? Now, this is going to be simple voltage division, pretty much. If you look at this, take a look at this just based on what you know. The voltage, if this is Z naught over 3, right? And at this point on over, it's 2/3 Z naught. Do you all agree with me, class? Let me try to do it this way. Here's what I'm really trying to say is, if I have this being plus to minus V1 plus, I come down here and I have Z naught over 3 right here, right? Now, break it off in parallel. Now I have Z naught over 3 here. Comes down, this is Z naught over 3 here. And then I have port 2 here. And this would be V2 minus coming out this way, if you will. And then and that's Z naught here. And then I have Z naught here. And this is going to be port 3. And here, coming off, I have plus to minus V3 minus. Do you all follow me on what I'm trying to say here? I'm just doing this with the resistive network so it's a little more obvious. Follow me? Because all this is voltage division at this point, because the transmission coefficient is 1. Is everybody with me on this? All right, now, if I want this voltage, right? First, I know, just from voltage division, if this is V1 here, right? The voltage at this point, because the actual net impedance from here to here is 2/3 Z0. Do you all agree with me that, class? So that means this voltage right here would be V1 plus, and then it's going to be times 2/3 Z0 over 2/3 Z0 plus 1/3 Z0, or just Z0. And what that means is this is going to be V1 plus over or times 2/3. So that's the voltage between here and here. Please just follow me on this one. It's not hard to see. Just be aware. Does everybody agree with that? Now, if I have 2/3 V1 here and I want the voltage here, then I do voltage division again. Do you agree with me? So I can say that V3 minus is actually going to be this voltage right there, which is 2/3 V1 plus, and then I'm going to go ahead and multiply it by Z0 over Z0 over 3 plus Z0. I did it on purpose, writing it out so you can see everything I'm doing in my head. All right, I'm not going to combine it. Does that make sense to everybody? It's simple voltage division again. Agreed, everyone? Now, you can see that that means V3 minus is really 2/3 times, and this is going to be 4/3, or inverted it's 3/4, right? The Z0s cancel, and then I have V1 plus. Does everybody agree with that? Class?
Why did you get 2/3 C naught for that voltage divider right there?
Well, I need the voltage from here. I need the voltage here, and it's going to be what? It's going to be Z0 divided by Z0 plus Z0 over 3 times that voltage, right? And the voltage is already down by 2/3. That's the reason. Which means ultimately that this voltage is simply 1/2 V1 plus. And that means V3 minus over V1 plus, which is going to be S31, is equal to 1/2. And that's also going to be V2 minus over V1 plus will be S21, and that's going to be 1/2 as well. So the transmission coefficients for both port 2 and 3 are 1/2 of our voltage divider. Agreed, class? Now, power is related, well, power is always related to the square of the voltage, is it not, class? Follow me on this? So, when I look at the power coming out port 2 or port 3, here, say, if I want the power P2, P2, and call this P3, really what I want to do is take the actual, it's the forward gain, if you will, the F21, F31, square that value and multiply it by the input power. Does it make sense what I'm saying? Everybody understand that? If this is a ratio of output voltage to input voltage, if I wanted the output voltage, I would take V1 times 1/2, whatever V1 was, right? Now, output power would be what? V1 times 1/2 squared, right? This is assuming you're going to be normalizing for Z0. So the whole concept of this, the power is always S31 or S21 squared times the input power. So that's the forward power gain. Does this make sense what I'm saying? I could go ahead and break it down and say, well, we'll get V squared over Z0 divided by 1/2, but the Z0s cancel and all these things. All right, so if we have an input power of 10 milliwatts to this right here, if we put 10 milliwatts in, then the output power here would be input power, Pn, times magnitude of S21 squared, and the output power here would be Pn times magnitude of S31 squared. Well, in both cases, that's 1/4 times the input power, isn't it right, class? So the input power was 10 milliwatts. So this is going to be 2.5 milliwatts. And this will be 2.5 milliwatts. So what happened to the other 5 milliwatts? It was dissipated by the resistances. That's the whole point. These things burn power up left and right, but they prevent reflective losses. Can you tell me the answer to that one? I know this is going to be the answer, but I think he doesn't ask for anything else, does he? Do you have the answer right there? But you all follow me what I'm doing? Power is related to you take the forward gain, either S21 or S31, square it, and then you got to take the magnitude squared, all right? Don't do a phase angle business. Take magnitude of that squared, and then you'll get it.
Which problem?
I don't, what problem?
It was 1037. Okay. Yeah.
All right, does everybody understand that? And maybe I should be clear about this. For these things, in general, the P out of any port in, is always going to be Sn times 1 if it's an input power squared times P in. That's the way you always do it. You take the magnitude squared of S. And that really was one of the things I was hoping you'd catch, but I understand there was a test today and probably everybody's dropping behind in things. They got projects and other stuff. Now, I want to tell you, S parameters aren't tricky. Make sure you know how to do power. You know how to get S parameters. If I give you a simple network like that and I ask for S parameters, I'd expect you to know how to get it. All right? To be complete about this, you all realize that S11, S22, S33 are all 0 because the reflection coefficient is 0. You all got that, class? Now, the rest is S. When you look at S21, S21 and S31, they are the same, right? You're going to take a look at this. You're going to realize a whole bunch of them are the same. What if I look this way? Doesn't the network look the same? So that means S12, S13 are the same. They're all a half. In other words, everything inside there except the reflection coefficients is a half. Do you follow me? You got that, class? Go through it one time with yourself just to make sure. Yes, sir.
So I assume you can expand that up to an arbitrary number of branches with diagonals, all zeros, and you get 1 over.
That's right, if they are impedance matched. And that's the key, because what would happen if it wasn't 3? Suppose I put 4 up here. A very good question, by the way. Suppose I had 4. Now how is this going to change? Probably Z naught over 4. As a matter of fact, you're going to have to do this mathematically. You prove it to yourself, all right? In general, the idea is if you're using, and I don't like resistive dividers because you lose power left and right. The only reason they do this, it's cheap, and if you don't care if you lose some power, as long as you don't get reflections, you'll do it. I'm going to tell you one other thing, too. The benefit about this particular divider, even though it stinks in terms of power loss, the thing is it's wideband, frequency independent, all right? Now, a Wilkinson divider that he talks about later, right in the next part, Wilkinson's divider have much better power coupling, but the problem is they're frequency dependent. They work at only one frequency. So for instance, if you try to Wilkinson's divider with your splitters that you have for like whatever, Spectrum Internet or something like that, that'll work great at one frequency, but the bandwidth on those things is usually very poor. So depending on the spread in frequencies you're going to have, you'll probably get really crappy coupling at some of the at the extended range on either side of the max. Does anybody know if the standard power couplers not power couplers, but splitters they give are, I think they're resistive, but I haven't torn one apart. Has anybody torn them apart? I think they're resistive. Now, there's another way they do this, too, and they don't do this in a book. You see, if you don't want to lose any power, what you can do is this. Now, this takes some real estate, you might say. If you've got a 50 ohm line and it feeds two 100 ohm lines, that's impedance matched if the 100 ohm lines are in parallel. Does that make sense to everybody? Right? But then when you got a 100 ohm line, now I've got a signal split. You follow me? No power loss there. But the problem is now I got to get it back down to 50 ohms if I'm feeding 50 or 75 or whatever. Now to do that is a problem because you're going to have to split it down. There's some way where you're going to lose power. And what they have is something called a balun. It's a balanced loading thing that's really a wideband transformer. I don't have time to cover it in here. I cover it in EMC. But there are tricks, other tricks you can do to match those things with low power loss and have a fair amount of bandwidth. Wilkinson's dividers give horrible bandwidth, though. It's only for one frequency. And I'm not even going to test you on Wilkinson. So I know I'm going to get questions, what are we responsible for? Up through this, like the resistive coupling, and if I give you any kind of standard, you know, if I give you an inductor in series with a resistor and I want the S parameters of that just like before, I'd expect you to know how to get them, all right? Everybody got me on that? So that's about where we stop. I'm not going to do any of the Chebyshev filters, the higher order filters, but I do want today, unless there's do you have another question about the homework that you didn't do? Nothing? All right, you're not going to get Wilkinson dividers, and 3 or 4 ports, it doesn't matter. Just realize the way you're going to have to analyze these is, I asked for you for the S parameters. Think always about what goes out and what comes in. And if they are not impedance match, if it's a 2-port and it's not impedance match, then you have to get the reflection coefficient to get the transmission coefficient. Got that? Okay. I wanted to go through the Emag, the earlier Emag stuff, because you haven't touched this in probably 15 weeks, right? All right, now I want to tell you, the stuff that you're going to be asked about, is not going to be some minor point. It's major themes. For instance, capacitance, electric field from a long wire of charge. I'm going to just tell you this right now. I'm going to put them up there. They're the major themes. Ampere's law, Gauss's law. All right? Standard things, capacitance and inductance. The major themes. I'm not going to test you on transmission lines because I'll get that question. Do we need to bring Smith chart? I'm not going to test you on transmission lines. All right? You're going to get matching using the stuff that we did for the microwave. All right? Where you're going to have the actual rotated circle, but I'm not going to test you on transmission line matching, stub tuning. Okay? Even though I could, I'm just telling you ahead of time, I'm not gonna. So what am I going to test you on? That's where we're going now with what you're responsible for, and they're the major themes. And by the way, if you've had a good physics course, most of you know this already before you even took Emag. When I was coming through, and I was an undergrad, I was really blessed with some incredibly good physics professors, and one of his name was Hagenbuch, and he always gave me some insight into problems, the way he thought about them. I try to do that when I'm teaching. I try to tell you what I'm thinking to solve a problem. And I actually had another guy. This guy's name was Foote, and he worked on the Manhattan Project. How many know what the Manhattan Project is? He was there when they actually created the bomb, and he didn't have a lot of good things to say about it. I don't think he frankly liked the idea he couldn't talk about it, because that's ultra top secret classified stuff. To this day, he can't tell me where he worked, how he worked, what he did. Just said I was there. That was interesting talking to him. Ask him anything, I don't know. So, now, major themes. First, I like to go to electrostatics. All right? And and we're going to go through the 3 basics. This is electrostatics. So with electrostatics, first thing, if you have a point charge Q, if you don't get this one, if this is asked, then really, you got to think about, do you really want to continue in this mention? If I'm a distance r away from it, and I asked you for the electric field strength, this is going to be vector r, actually. Let me put vector r here. Well, the electric field strength here is simply the magnitude of the charge over 4 pi epsilon naught, if it's in a vacuum, magnitude of r squared times ar. Now, ar is a unit vector in the direction pointing away from the charge. If the charge is negative, the sign takes care of the actual direction. Now, how do you get r? AR. The unit vector AR. Y'all familiar with that symbolism, right? A sub r is a unit vector in the direction of r. The normal way to get it is just take the vector r over the magnitude of r. Believe it or not, people will make mistakes on that, usually because they're tired. So a simple example of this, just so everybody understands what I might ask. If I said r vector was equal to 10ax plus 3ay, and that's it, and I wanted you to get ar for that equation, if that's my r vector, then that would be 10ax plus 3ay divided by, since it's magnitude, square root of quantity 10 squared plus 3 squared. That would be AR. I left it that way on purpose so you can see what the process is. There's nothing tricky about a unit vector, so don't stumble on these. But people will. Yes?
So this would be a Gauss law question?
No. This is fundamental. This is called Coulomb's law. It's the most fundamental point. And everybody that had basic physics should know this. One of the things you're going to see is epsilon naught. People, believe it or not, will struggle with that one. I'll give you that. One of the easy ways to do it, and Whitmore's book's good about this, just leave epsilon naught as 1 over 36 pi times 10 to the minus 9. The units are farads per meter. That's really approximately, this is about, what, 8.54 times 10 to the minus 12 farads per meter. You can use that too. This will cancel a lot of pi's usually. The 36 pi will cancel a whole bunch of things. Y'all remember seeing it that way, both ways? Just showing you some things. So that's basic. That's a point charge. The next basic thing you see is a line charge. So if you have an infinite line of charge, and then I'm going to say it has a charge density rho L, and I come off a distance, and he likes to use rho for the vector distance in cylindrical coordinates. Y'all remember that? Then the electric field points away from the line, wherever it is. It could be on the x-axis, y-axis, z-axis. It doesn't matter. It points away from it, right? And the actual electric field out here, this would be from the line charge, would be equal to the actual line charge density, we can get this with Gauss's law, over 2 pi epsilon naught, and its magnitude of rho in the a rho direction. Now, a rho in this one can trick people because a rho does not mean necessarily it's in the rho direction. For instance, if this thing's on the x-axis, then that a rho is deceptive, and he doesn't really go into a lot of things to clear this up. But let me just say this a rho is equal to whatever vector this is. And I'm going to give you a concrete example so you don't trip up on this one. So whatever that rho is over the magnitude of that rho. Now I'm going to give you an example so you understand exactly why I did that, all right? And this is a common thing. People, they have trouble with this one. So you're used to seeing line charge z-axis, right? Now line charge is not z-axis. All of a sudden, I do this. I'm going to have the line charge. This is going to be x. This is y. And I'm going to have the line charge coming out of the board in the z direction. I am going to have it in the z direction, but it's going to be displaced by an actual value of 2 meters. So if that's the x-axis here, this is going to be intersected x equals minus 2, and that's where that line is laid down. Can you all follow me on that? Let the line charge be rho L. And now I want the electric field. Where I want the electric field becomes critical. So please watch this. I want the electric field at a point, that's 2 meters away, but I want it up 2 meters. So I want the point on the y-axis 2 meters high. I want it at the point x equals 0, z equals 0, y equals 2, or 0, 2, 0. So I want to know what the electric field is here. And this is at point 0, 2, 0. Can everybody follow me in this one? Now please watch this. So the way you do this problem always, you draw perpendicular, the shortest distance from that line charge to this point. That's your rho. Got it? You go from the line charge directly to the point of observation of the electric field. Now to get that rho, and make sure you do it this way, it's the perpendicular distance, it's the shortest distance from here to that line charge. Remember that, the shortest distance if it's an infinite line charge. Got it? Here's how you always get it. You always take, and let's do it in Cartesian coordinates. Don't even bother with, you don't need cylindrical for this. All right, you take the coordinates of the point of observation you're going through, minus the coordinates of where you came from, and ignore the one where it has the infinite extent. And I'll go through this. So if you look at this with the x coordinate of the point of observation, it's at 0, right? So it'd be 0. Do y'all follow me? That's at x equals 0 there, right? But what's the x coordinate of the actual charge that caused the field? -2. So it's 0 minus quantity minus 2. It's always coordinate of point of observation minus coordinate where charge exists, and you subtract them, right? And it's in the ax direction. Plus, now what about the y coordinates? Y coordinate here is 0, so it's 2 minus 0. Ay. What about the z? What did I tell you? Ignore the infinite coordinate, right? Because it's all up and down z at z equals, on the z-axis at x equals -2. Correct, class? So you ignore that coordinate. This is row vector here. So what is it really? That's simply 2ax plus 2ay. By this time, most of you can see that's what it's going to be for the vector. I went over 2 in x, and I went up 2 in y to get to that point. Correct, class? All right, so therefore, what is a row for this one? Remember, a vector over magnitude, it's 2ax plus 2ay over, and the magnitude is going to be what? 4 plus 4 square root, or square root of 8. You can leave it like that. Do you agree with that? You're going to take 2 squared plus 2 squared, right? Everybody see this? That's the vector direction. So you can get the electric field there very easily because now you have that, and you just plug in rho L over 2 pi epsilon naught, whatever rho L is, right? Magnitude of rho you've got, and now you have a rho too. Agreed, class? How many see this right here? Any questions about this? I want to show you how to make sure you get unit vectors correct for this one. This is the one that gets people. It's always the line charges where they mess up that unit vector. Now the next thing is an infinite plane of charge. And then we get into capacitance. I'll talk about Gauss's law too. Do most of you remember this, by the way? If you do, give me a show here. This is coming back, right? It's not something distant. All right, next thing is the infinite sheet of charge. So an infinite sheet of charge, let's say this is going to be at a point, it's at x equals 0, and it's in the, no, let me put it to you this, let me do it this way. If this is the z-axis, this is at x equal y, it's in the xy plane, just put it that way. In xy plane. So we have an infinite sheet of charge there. And the value is rho s. And I want the electric field above and below the plane. Now the thing about an infinite sheet of charge, the electric field in general is given by this. E for a sheet of charge is always going to be equal to rho s divided by 2. Now that's an infinite sheet of charge with a certain charge density, and that would be coulombs per meter, and a direction A normal. A normal is pointing away from the charge. I'm going to do this problem a couple ways so that there will be no mistake in how you get this. If I give you an infinite sheet of charge in the xz plane, so call this z, let x come out of the board and this be y. So here's my infinite sheet of charge, rho s. It's a surface, so the charge is like this, right? It's coming out of the board. It's an infinite thin sheet of charge in this direction and that direction. If I'm on this side and I want the electric field here, well, I know the magnitude is rho s, right? 2 epsilon naught, pardon me, over 2 epsilon naught. I gave you the D field. There's an epsilon naught here. And it's in the anormal direction. Well, the normal points away from the infinite sheet, which would be what direction there? Positive AY. That would be what it would be over there. But if I was on this side of it, then the electric field would be what? Say, yeah, it would actually be minus rho s over 2 epsilon naught in the AY direction. It's going to have the same magnitude but the opposite direction. Do you all agree with that? What happens if I take the plane and I put it here and I put it in the XY plane again? Above it, it would be positive AZ. Below it, it's negative AZ. Got me on this one? If I tilted it like this, then it's going to be whatever that direction is. If it's a 45-degree angle, it's just 1 over square root of 2 times AX plus AY, right, times rho s over 2 epsilon naught here. On this side, it would be minus that. Do you all agree with me? So you get the general idea for when you have infinite sheets of charge. Now, after that, I'm mentioning Gauss's law. And I'll put it here. Gauss's law. The easiest way to state it is in the integral form, not the differential form. There are 2 forms of this. One is the differential form. Divergence of D is the volume charge density, and you should know that one. And the other, or at least be familiar with it. This is, you're given a D field, you take the divergence of it to get rho s, or rho v, pardon me, the volume charge density. The second thing is, this is the integral form of it. The integral of D dot ds over any closed surface is really the integral of rho v dot dv over the volume, and that's really just equal to the total charge inside the surface. Y'all agree with that? Now, the typical questions you get are for cylindrical or spherical symmetric problems. I'm going to do a simple one just so everybody understands the kind of thing that you're responsible for. If we did it in spherical, say we do this in spherical coordinates. And I'm going to say I have rho v equal to 10 to the minus 9th over r for r greater than 0, less than a, and rho v equals 0 else. And then I want the E field, or better yet, I want the D field for all r. So I want it for both r less than a, r greater than a. Now, most of you probably, if you've had Wentworth or myself or Riggs for this, you remember the way to do this. First thing, you identify what's called the Gaussian, really, I call it the Gaussian surface. It's the air is something that's going to be a symmetric surface that's encasing that charge, right? If it's a cylinder charge type thing, then it would be a cylinder. If it's a sphere, it would be a spherical surface. That or Gauss's law won't work. In this case, it will, because if it's 1 over r, it means it's symmetric about r. So if we take a look at this, and let me go on this board back here to do this problem. We're going to go for r less than a, greater than 0 here. We're going to do this. So Gauss's law says the integral of d dot ds over the surface that's closed is the integral of rho v dv over that surface. This is the most general form. Now, something I'll tell you too. I'll give you the divergence, the curl, the gradient, and the Laplacian for the different coordinate systems. All right, so you won't have to worry about memorizing any of that. When I do this one, when I take an integral of d dot ds, what I'm really going to do is say that if I'm looking at this charge distribution, I'm coming out a distance r, and I'm saying I make a surface there, and I know the integral of d dot ds over that surface is equal to the charge enclosed, right? Now, the smart way to do this, since basically you're only going to get spherical or cylindrical coordinates, is multiply the surface times d. Here, for this one, if it's a sphere, what's the surface area of a sphere? 4 pi r squared, right? We could write it out. If you want to write the integral out, you can, but it's kind of a waste of time. This is going to be simply 4 pi r squared here. Then it's times the d field. Now, the d field is going to be in the radial direction only because of symmetry. Are you with me? I'm not going to spend a lot of time reviewing symmetry, but And what's that equal to? It's the total charge enclosed. Now this one is not a constant charge density, so you can't take the charge density times the volume. Follow me? If it was a constant charge density, you could just take charge density times volume and get it. Do you follow me in this class? Here we've got something that isn't constant. It varies with R. So now you've got to do the integration. You have to go down and say, well, it's a triple integral, right? And it's of rho v, which is 10 to the minus ninth, over R. Now it's times the differential unit of volume. I'll give you this one too. Does anybody know what the differential unit of volume is in spherical coordinates? You're right. It's R squared sine theta d phi dr. Remember that. I'll give it to you, but people mess this up. I often see just R and the sine theta is gone because they're getting confused with cylindrical. This happens a lot. So for this one, first is where does theta go from? Theta. 0 to pi, right? That's theta. It's the one vertical line. Phi goes from, right. And R goes from, exactly, 0 to R. And so somebody should yell at me and say, well, technically you should prime those. Yeah, I should, but I'm an engineer. I'm not publishing this thing. I'm just getting it done. So follow me on this. I don't care if I integrate it out in R and still substitute it in R. It doesn't irritate me. It will the math department. Over here, now you all see one of these R's cancels, right? So I get rid of one of them. I'm left with one of them. Do you all agree with me? All right, now the first thing is when you integrate, I'm going to do this kind of quick. I know what I'm going to get for dr right here, and I'll put it here. Dr is going to have a 1 over 4 pi r squared here. And the reason I know this, I'm going to take this term and have it go right there. All right, I'm going to divide both sides by it. Does that make sense to everybody? After I do that, now I've got to evaluate this integration. When I integrate from 0 to pi, well, I integrate d theta, right? Well, sine theta integrated is minus cosine theta, correct? Minus cosine theta integrated at pi is going to be what? Minus 1. So it's minus a minus 1, or 1, right? Then it's minus the cosine. It's minus a minus cosine is 0. It comes out to be 2. I've done it too many times. So this is 2 right there when you do the sine theta integration. What about phi from 0 to 2 pi? There is no phi in here, right? When I integrate d phi, I get phi, right? And I evaluate it at 2 pi, which is 2 pi, minus 0 is 0, so it's times 2 pi. Finally, I integrate r dr. That's r squared over 2, correct? And I also need to be careful to put the 10 to the minus 9th there. So now I have r squared over 2 from 0 to r, or it's just r squared over 2. And that, in fact, is the right answer for r less than a greater than 0. Now, you all see you can clean this up. All right, you can cancel. I'm going to cancel a few things. Let me cancel the pi starters. Then I got 2 pi 4 there. I'm going to get rid of all that. Then I've got an r squared. Get rid of that. Right? So I have this. And the nifty thing about it, it's constant. If you look at that. Follow me? It's a constant. All the way out to a. But once I'm at r greater than a, what happens? Well, then you have a finite amount of charge, right? When you go for r, now I come here and I'm going to say for r greater than a, here's a. There's where all my charge is, right? Correct, class? So now when I come out here and I do this, the integral of d dot ds equal to the integral of rho v dot dv. Well, this is still 4 pi r squared dr. But on this side, now we only integrate out to a. Correct, class? So when you integrate out to a, when I do this instead of r, you're going to end up with, this is going to be 4 pi, right? And then I'm going to have r squared over 2 evaluated from 0 to a. And that means that's going to be 4 pi a squared over 2 times 10 to the minus ninth. Or finally, when I look at that, I get d of r here equal to 1 over r squared. Now this one will vary as 1 over r squared. The 4 pi's cancel over there, and I have a squared over 2, and I have 10 to the minus ninth, and that's going to be for r greater than a, and that's d of r. That's how you would do a simple Gauss's law problem. You probably get something like that, maybe a cylindrical one, something not too hairy, but straightforward, all right, like that. Now, after that, briefly, capacitance, I want to just mention. For capacitance, in general, it's always Q over, really, let me do it this way. In general, capacitance times voltage is equal to charge. The standard way you do capacitance problems is assume a charge density and find the voltage between the plates. Do y'all remember this? I've got 5 minutes left. I'm trying to make the best use of my time. How many remember doing that for capacitance problems? If you have any problems, ask me. It's straightforward. You assume Q, get D. After D, get E. After E, integrate E to get V. Then take simply Q by V, and you get the actual value of C. That's it. And in general, you can add capacitors in series, add like resistors in parallel, right? Capacitors in parallel like resistors in series. You just add up the value. Now, now we talk about the actual magnetic field. And in general, I'm going to put these relationships down that you need to know. J is equal to sigma E. J is the conductivity. E is equal to epsilon times, or I'm sorry, B is equal to epsilon times E. Epsilon is the permittivity. B, this is the magnetic field intensity, is equal to mu times H. Mu is the permeability. These are relationships you're going to need to be familiar with and acquainted with. And after you have these 4 right there, divergence of D is equal to rho V is important also. All right, that's the actual form of Gauss's law that's most common. The divergence of B, does anybody remember this? If the divergence of D is charge density, right? Electric charge density. Divergence of B should be what kind of charge density? Magnetic charge density. Is there such a thing? No, it's 0. Not in the macroscopic world. No, it's 0. Now that means also that the integral of B dot ds over a closed surface is 0. They're one and the same. Saying one implies the other. Getting back to it, we had Gauss's law that said the integral of d dot ds is equal to charge inside. The parallel to that in magnetics is Ampere's law. It says the integral of h dot dl around a closed loop is equal to the actual current penetrating the loop. Do you remember this? I'm closing this. I normally do about 45 minutes of review on this stuff, but I think I do most of the time. I don't think I go a full hour. So this one, I'll tell you, this is the one more people have trouble with, I think. Here's the formula for it, what it states. It says the integral of h dot dl over closed loop, and you only use this, and this is Ampere's law. Is equal to really the integral of j dot ds, but really it's the I enclosed by the loop. Where this always happens to be useful is when you have cylindrically symmetric problems. You almost never use Gauss's law for anything but a cylindrically symmetric. You can for an infinite sheet of charge, but you don't have to for that one. So when we look at this, the classic example is if I have a current I on the z-axis, and I come out a distance rho, and my purpose is to find the H field, right? Well, if I have a current I in that direction, we know by the right-hand rule that H is going to be in the phi direction. Do you agree with that? Class, y'all remember this? H always circulates. So you put your thumb in the direction of current, your fingers show the direction that the actual H field will be in, right? And it's going to be perpendicular to this radius vector. So it's going to be that way, perpendicular to the head. Now the H field is, we call it a circulation type of field. That's H. The integral of H dot dl is over here. I could write it down, but it's really, H isn't going to change in magnitude anywhere around there if it's a symmetric problem, and it is, right? I've only got one line charge, it has to be. So this is really just the perimeter, or it's going to be 2 pi rho, where rho is going to be a magnitude of the radius, times h phi. That's equal to the current penetrating the loop. This is where people have trouble. When I say penetrating to the loop, just think of all the current going up inside that loop if it's symmetric. There's only one, it's I. This is probably the easiest way to get the H field instead of doing the integral, right? If it's infinite. That means h phi for this one is simply I over 2 pi rho. It's in the a phi direction. Now, that can be expanded. Instead of having just the current, singular current, I can have a pipe of current. All right? Where now this has a current density J right there. And now what you have to do with this one is you have to break it into two regions. The regions inside the pipe, where if the current density is constant, where you come out and you come a radius away from there, but inside the outer radius. And then you say all the current that penetrates that is equal to the integral of h dot dl around that. Follow me? Which means this part of the integration never changes. The thing that will change is the amount of current that flows through that. Got that, class? And that's the big deal with that. One last thing I've got to tell you about, this is going to be with inductance. I'm not going to ask you anything crazy about neither inductance or capacitance, no bizarre problems. But if I asked you for the mutual inductance, this is a tip, take it for what it's worth. If I had a current I1 here that's infinite and a current I2 here, and I want something about the magnetic flux that penetrates between that space, that's a fair problem. Got it? I could also say if I2 went this way, the amount of flux through there. I could also ask what is the mutual inductance per unit length of that problem. I'll try to finish this up on Friday, right? So these are mutual inductance problems you haven't seen. I'm going to do a couple with EMF on Friday, and I'll do a wrap-up, and I'll take all your questions about the final on Friday. Fair enough? Now, the last thing is this. I'm getting tons of these emails in different forms. When do you need this project? I've already have some of the people send me their final form of the projects. I want a printed copy from each and every one of you signed, all right? I want your name, I want a signature on it. Staple as many pages as you want to be handed in to me. I need that. But send me the electronic copy as well, and I thank you. Any other questions? Listen, we're wrapping this up. I'm trying to be very clear about some of these things, and if you've got questions about what's on the final, I can tell you, if you look at the last test especially, it's reflective of what's on the homework. Just look at it, all right? It's not going to be coming out of left field so much. It's straightforward stuff. The hardest part about the final, really, is just getting enough sleep. Most people are so sleep deprived, they make mistakes that they can't believe they made. A lot of